All right, good morning. Good morning, everyone. Welcome back. Just a quick announcement before we start the session. Tomorrow, Wednesday evening at 6 p.m., Steve Schenker is giving a public talk. If you wanted to attend, please go on the website and register. You'll find the link on the Strings 2025 website. Also, for the outing on Thursday, you should find the registration link also in an email that Sundar sent. We will most likely resend it sometime today. Please also register for that if you want to come. You also need to select what kind of food option you prefer. So it's really great to have that ahead of time so we can organize appropriately. And with that, let me hand it off to Tom.
Okay, hello everyone. So welcome to the second overview session and panel session. And it's my honor to introduce Edward Witten, who will start things off with an overview of algebras in gauge theory and gravity. Okay.
Thank you, and thanks first of all to the organizers for putting together this wonderful conference and for the invitation. Can you just in the back confirm that you can hear with the microphone? Okay. So I see a slight misprint that was meant to be algebras in field theory and gravity, but gauge theory will do. So quantum mechanics textbooks usually envisage a quantum system probed from the outside by an observer who is looking at the system but isn't part of it. As observers in the universe, we're in a different situation. We're part of the system that we're trying to observe. Moreover, we can't resolve the quantum microstate of the universe, and that's not only because of technological limitations, but also because we cannot see beyond the cosmological horizon. So some of standard textbook quantum mechanics doesn't quite apply. I'm going to assume that a few ingredients of standard textbook quantum mechanics are valid. So first of all, I'll assume that observables form an algebra A, meaning a vector space. You can add or multiply observables. You can multiply an observable by a complex number, and they have an associative multiplication law, like operators on Hilbert space. I'll assume that there's a notion of Hermitian conjugation of observables, and I assume what we measure are expectations of observables in the state of the universe, however that state of the universe is to be understood. And I assume one more thing, which is that positive observables have positive expectation values, meaning that if I denote the expectation of an observable A with this symbol with the brackets, then the expectation value of A dagger A is non-negative for all A. That's actually enough to imply that our observations can be described by a Hilbert space, although it wouldn't be necessarily a Hilbert space that describes the whole universe. We just formally introduce a symbol psi equals psi1 that represents the presumed state of the universe. And then for any observable A, we introduce a symbol psi sub A that represents A times psi. It represents the state of the universe after acting with A. Then inner products are defined by saying that the inner product of psi A with psi B, I hope most of you can see the green dot, is the expectation value of A dagger B for any two observables A and B. Now, because of the positivity assumption on the last slide, this definition is consistent with all the properties that Hilbert space inner products are supposed to have. So we actually get a Hilbert space after we divide by null vectors and possibly take a completion, because Hilbert spaces are supposed to be, in a certain sense, complete. Now, that doesn't mean that H describes the quantum state of the universe. It does describe all measurements we can make, but it was constructed with no knowledge of what was beyond the horizon, if there is a horizon. So it will give us no information about what's beyond the horizon. It's not a Hilbert space for the whole universe, but it is a Hilbert space for us. Since we can see distant galaxies, the action of our algebra A on H contains information about distant galaxies, but it doesn't contain any information about what's beyond the horizon. Even from a complete knowledge of how the algebra A acts on the Hilbert space, which is highly idealized compared to what we can actually learn from experiment, we will learn nothing about what's beyond the horizon. So there is a sense in which it might make sense to talk about entanglement wedges of gravitating regions, such as the region of space-time that we on planet Earth are living in. But some knowledge of what's beyond the horizon is needed to predict an entanglement wedge beyond the horizon. Well, what kind of algebra is the algebra of observables accessible to us? To get a simple answer, we need two steps. First, to get a simple answer, we have to assume that what we measure are bounded operators. A mathematical reason for this assumption is that bounded operators can be multiplied. So if our observables are bounded operators, they do in fact form an algebra. By contrast, it's problematical to multiply unbounded operators in general. But there's a physical reason for considering bounded operators, which is that in practice, even if we measure something that in theory is unbounded, like the electric field, we only measure it in a certain range. So in practice, our measurements do seem to be measuring, for example, in that example, a bounded function of the electric field. So although this discussion is an idealization, it seems that assuming what we measure are bounded operators is reasonable physically, as well as a tremendous simplification mathematically. There's one more step needed to get a simple structure theorem for A, and this is roughly, we do not try to distinguish operators that can't be distinguished by experiments. More precisely, consider a sequence of observables, A1, A2, and so on, with the property that for all states psi chi, the matrix elements of AN between those states has a large n limit. If so, then we define an operator A whose matrix elements are given by those limits, and we say that A is the limit of that sequence, and we consider A, this limit, to be part of our algebra. Mathematically, this is called a weak limit. Physically, the logic is that an experiment measures finitely many matrix elements with finite precision. So under the hypothesis I stated, no experiment will distinguish A sub n from A if n is sufficiently large. So for experimental purposes, A is in fact the large n limit of A sub n. Finally, physically, it's well motivated, at least in a closed universe, to assume that the center of the algebra consists only of complex scalars. In an open universe, if the observable region goes off to spatial infinity, there might be gauge charges that would make us modify the statement, but I'll assume today that the center consists only of complex scalars, as we would expect in a closed universe, for example. Given A and B, the algebra is what's called a von Neumann algebra, and C makes it a factor, the analog for algebras, of a simple as opposed to a semi-simple Lie group. So such von Neumann factors have a simple, roughly speaking, a simple threefold classification, which is as follows. First of all, if A has no useful simplification beyond the axioms, then that's an algebra that's said to be of type 3. So with the type 3 algebra, you can do quantum mechanics because I incorporated enough axioms so that quantum mechanical probability, interpreting measurements in terms of expectation values of algebra elements makes sense. So a type 3 algebra gives us enough to do quantum mechanics and no more. There actually are theorems showing that out of all von Neumann algebras, a generic one is of type 3. So one version of this statement is in this paper. So that's natural. It says that if we're given the axioms A, B, and C, nothing useful follows beyond that. We can do quantum mechanics and that's it. There are two kinds of simplifying properties the algebra might have, in which case it's said to be of type 2 or type 1. A type 2 algebra has a trace but no irreducible representation. A type 1 algebra has an irreducible representation. So those are the two important special cases of algebras that have useful properties beyond the axioms. By a trace, we mean a complex valued linear function on the algebra, which I'll denote as trace A, that obeys two properties. The trace of AB is the trace of BA, and the trace of A dagger A is non-negative for all A. The trace doesn't have to be defined for all elements of the algebra, only for a sufficiently large, dense set. For a type 2 algebra, the function trace is not a trace in a Hilbert space representation of the algebra. a type 2, any von Neumann algebra has Hilbert space representations, as I explained at the beginning. But a type 2 algebra, the trace in a Hilbert space representation of a type 2 algebra is infinite. The function that I call the trace is a sort of renormalized version of a Hilbert space trace with an infinite factor divided out. An algebra of type 1 has an irreducible representation in a Hilbert space H prime. This H prime is not necessarily the H that we constructed at the beginning in an abstract way to incorporate observations. We defined at the beginning Hilbert space, and we completed to get a von Neumann algebra, and that algebra might be of type 1, and if so, it'll have a irreducible representation H prime, which will not be the one we constructed by the general procedure. Then von Neumann showed that A is actually the algebra B of H prime of all bounded operators on H prime. And then there's a natural trace, just the Hilbert space trace in the Hilbert space H prime. It's not defined in all elements of the algebra. Assuming H prime is infinite dimensional, the trace of the identity is plus infinity. But it's defined on a dense set of, well, on a large subalgebra of operators said to be of trace class. For either type 1 or type 2, once there's a trace, we can define density matrices. If H is any Hilbert space representation, which could be the minimal one that we described earlier at the beginning in an abstract way, or maybe a bigger Hilbert space that includes degrees of freedom beyond the horizon. So at the beginning, I described a Hilbert space that was sufficient for our observations, but someone else who did somehow have access to the whole universe maybe would have used a bigger Hilbert space to describe the whole universe. But in any case, given any Hilbert space representation, a density matrix is an operator in the algebra that obeys the usual condition of a density matrix. Except that now trace, what I'm calling trace, is not a Hilbert space trace. It's this, in the type 2 case, it's this more abstract trace function. It's not hard to prove for both type 1 and type 2 that such a density matrix always exists. It's a positive operator that, roughly speaking, is an element of A. There's some fine print. And it has the standard normalization condition of a density matrix. If psi is a unit vector, then the trace of the density matrix is 1. So the density matrix, just as in ordinary quantum mechanics, will be a positive element of the algebra with trace 1. Once we have density matrices, we can define von Neumann entropies or Rényi entropies and other functions considered in quantum information theory by standard formulas. Most of the definitions use only the axiom satisfied by the trace function, not the fact that it actually is a Hilbert space trace. However, there's an important difference between a type 2 algebra and a type 1 algebra. For a type 1 algebra, the trace is literally the trace in an irreducible representation. No renormalization is required, so the definition of the entropy is completely natural. For a type 2 algebra, there was an infinite renormalization in the definition of the trace. So this corresponds to an additive renormalization of the entropy. To check that, let's see that if the trace is multiplied by a scalar, then to satisfy the definition of a density matrix, we have to rescale the density matrix by the opposite factor. And the effect on the entropy is to shift the entropy by an additive constant, which is the same for all states. So the best we can say is that entropy in a type 2 algebra is defined up to an additive constant that's independent of the state. What are really well-defined are entropy differences. This is analogous to entropy in classical mechanics. In classical physics, entropy differences can be defined by integrating the first law. But there's no natural zero of entropy in classical physics, and no natural way to fix an overall additive constant. Type 2 algebras have a further bifurcation into two subtypes, type 2.1 and type 2 infinity. In a type 2.1 algebra, the identity operator has finite trace, and the trace function can be normalized so that the trace of the identity is 1. And more generally, the trace is finite for every element of a type 2.1 algebra. In a type 2 infinity algebra, the trace of the identity is infinite, just as for a type 1 algebra with an infinite Hilbert space. And the trace is only finite for a subalgebra of trace class elements. Now, what do we expect the algebra of observables for a given observer to be? First in quantum field theory, and then possibly with gravity. Well, the interesting case is an observer who, because of black hole or cosmological horizons, cannot see the whole universe or even a complete Cauchy hypersurface. If you can see the whole universe, you'll have access ultimately to a type 1 algebra of the familiar situation with an irreducible representation. The interesting case is when you can't see the whole universe. For example, here's a Penrose diagram of an observer in de Sitter space. As usual for Penrose diagrams, time runs vertically. And I've chosen coordinates so that an observer propagating on a geodesic lives on the left edge of the diagram. The left edge is the world line of the observer. And then the causally accessible region is this green wedge, bounded by past and future horizons. So in such a situation, one will not get a type 1 algebra, certainly not in ordinary quantum field theory, and not in gravity to the extent that we actually know how to do computations. The time-like tube theorem of quantum field theory, which is a sort of precise version of HKLL reconstruction, says that the algebra of observables that the observer can measure, the algebra of operators along the observer's world line, is the same as the algebra of observables in the whole causal wedge, shown in green. A heuristic explanation is that the observer can shine a laser beam at any object in the green region, and by seeing what is reflected back, can learn about what's there. So you can not just passively observe, you could passively observe something down here, but you can actively do experiments on something in the green wedge. And so it turns out in ordinary quantum field theory that the observables along the observer world line are the same as the observables in the green wedge. A classic result that goes back to Araki is that in quantum field theory, the algebra of such a proper subregion is of type 3. So the observer can do quantum mechanics, but can't describe those observations by density matrices or entropies, which are type 2 and type 1 concepts. The type 3 nature of the algebra has a dual in ADS-CFT that was studied by Liu and Leutheiser a few years ago in work that's influenced a lot of subsequent developments. So here I've drawn schematically the Penrose diagram of an asymptotically ADS black hole. So it's a two-sided situation. There's a left asymptotically ADS region and a right region, and a spatial hypersurface connects the two. And if you live on either the left or the right, you see past and future black hole horizons. And for example, an observer with access to the right boundary, the solid blue, the associated causal wedge is the light blue region outside the past and future horizons. So the blue wedge, as I just said, is the region causally accessible to the right boundary, the dark blue, where we imagine the observer to be making measurements. In the approximation of treating the bulk theory as a quantum field theory in a fixed background, the algebra of the light blue region is of type 3, so in an appropriate limit, that's also the case for the algebra of observables on the right boundary. The appropriate limit is when you completely turn off gravity and treat the bulk theory as an ordinary quantum field theory in a curved background. So if the boundary dual theory is an SUN gauge theory of some integer n, so for a definite integer n, the thermofield double state. So the natural state in this universe is called the thermofield double state. For some fixed n, first of all, the thermofield double Hilbert space is just a tensor product, HL tensor HR, of two copies of the CFT Hilbert space. And then, for fixed n, the thermofield double state is simply a vector in this tensor product Hilbert space. And for fixed n, the algebra acting on either h left or h right is a type 1 algebra with h left or h right as the irreducible representation. So for fixed n, the algebra accessible to the observer on the right is just the type 1 algebra of all operators on h right. That's a simple answer, but it has a drawback. The drawback is that for finite n, for n a definite integer, notions of space-time and causal structure are not precisely defined. So although we have precise quantum mechanics with irreducible action on a Hilbert space, for when n is a finite integer, puzzles about causality and so on in the field of a black hole, or similarly in cosmology, are not expected to be sharp when n is a definite integer. If we want to do quantum mechanics in a world where semiclassical notions of causality are meaningful and sharply defined, we need to take a large n limit. And then it's no longer true that the thermofield double state is a state in a tensor product Hilbert space. It's a state in if you're above the Hawking-Page transition, the thermofield double state is a state in a new Hilbert space that you can define, the thermofield double Hilbert space. It's a Hilbert space that describes states of the quantum fields in a connected spacetime. In that large n context, the causal wedge of the boundary is this subregion shown here. And the algebra accessible to the boundary observer is of type 3, as it always is, for this quantum field theory case of a subregion of spacetime. So even though for finite n, the right boundary would have a type 1 algebra, in the large n limit, it should be possible to define an emergent type 3 algebra. To define this emergent algebra, Liu and Leutheuser considered single trace operators normalized with no overall factor of n. For finite n, they would generate the type 1 algebra of the boundary. In the large n limit, they have divergent expectation values. So to get operators with a large n limit, you have to subtract their expectation values, say at some inverse temperature beta, which you choose to be above the Hawking-Page transition. And then the subtracted operators do have large n limits. And ADS-CFT duality, together with what's known about quantum field theory, says that the algebra that they generate is of type 3. Since it's the same as the bulk algebra of the causal wedge, treated as an ordinary quantum field theory at g equals 0. So the boundary algebra defined, as I tried to summarize in the top of this slide, is supposed to be dual to the bulk algebra of the causal wedge at g equals 0. Now, an important detail is that this large n limit of single trace operators does not contain the Hamiltonian. Keeping track of powers of n, you'll see that it contains h over n, but not h itself. And the subtracted version of h over n in the large n limit becomes, I wrote a C number, but I should have written that it becomes central. So in the large n limit, the generator of time translations is not contained in the algebra. Time translations act as an outer automorphism of the algebra. So we'll come back to that outer automorphism in a few minutes. But for now, we just note, following Liu and Leutheuser, that it means that in the large n limit, the operators in a time band of the boundary are a proper subalgebra. In fact, the boundary interpretation of this subalgebra is that it's the algebra of a smaller bulk region. So here, if I take a time band of the boundary, which is this dark blue, this partial dark blue, well, part of the right boundary that's been written as dark blue, the causal wedge is this light blue subregion, and the algebra of the light blue subregion will be a type 3 subalgebra of the algebra of the whole causal wedge. Similarly, although I didn't make a picture, we could make a semi-infinite time band bounded in the past but not in the future, and that would again give a type 3 algebra. So various properties of the bulk geometry and dynamics are reflected in properties of these emergent bulk algebras. I'll just mention a couple of facts which you might hear more about later from some of the panelists, although unfortunately their time will be short. We've already seen the connectedness of the two sides of the thermofield double is reflected in the type 3 nature of an emergent boundary algebra. There's an analog which you might think of as quantum connectedness between a black hole that's been evaporating for a long time and the radiation it's emitted. You can also give a criterion for the existence of sharp horizons. Even in the Stringy case, that means even when g squared n is not taken to infinity. So we don't expect a sharp definition of the horizon for finite n, but it's not so clear a priori if the horizon is a sharp notion when general relativity is replaced by string theory. So you can argue from this type of setup that at least in certain cases you can have a precise notion of a horizon. With finite g squared n, that means non-zero g squared n, that means a stringy situation, but in the large n limit. And there's more, which you perhaps will also hear of from Nima in his short talk later, on algebras associated to time bands and stringy geometry and chaos and other things. Now, there's a slightly different story if we consider a slightly different large n limit in which we include the Hamiltonian. But before explaining that, I want to give some heuristic reasons to think that type 2 algebras might be related to gravity. So, well, here we should imagine semiclassical gravity, where I imagine semiclassical gravity means any situation in which semiclassical notions of causality make sense, possibly incorporated to a stringy realm where you have stringy horizons, as I just mentioned, but not a completely quantum mechanical situation with finite n. The basic reason you might think that type 2 algebras are relevant to gravity is that in gravity it seems that we can define entropies even when we cannot define quantum mechanical microstates. So we've been grappling with that ever since the early days of black hole thermodynamics. A quantum theory with entropies but no microstates is a good candidate to be described by a type 2 algebra. So that simple reason is perhaps the most basic reason you might think type 2 algebras are relevant to semiclassical gravity. Somewhat more specifically, we often compute in gravity things that we call traces, even though they aren't traces in any way we understand. So we compute things that we call trace e to the minus beta h by a gravitational path integral. For example, in ADS space, we take certain asymptotically ADS boundary conditions with a circle at infinity of circumference beta, and we say the path integral with that asymptopia calculates trace e to the minus beta h, but the topology is wrong for the function we're computing to be interpreted in terms of a sum over states in any way that we really concretely understand. But anyway, we compute what we call trace e to the minus beta h, even though it's not a trace of any operator in any Hilbert space. And we compute more complicated things that we also call traces. So even though we don't have a Hilbert space H and operators on that Hilbert space, such that the quantities we compute really are such traces. So we call these functions traces because they obey the abstract properties of traces, namely these two conditions, which were the axioms I stated earlier for a trace. They obey these conditions for any O and O prime for which these quantities are finite, such as something like this. Now, typically, we believe we are computing large n asymptotics, not limits, because these quantities usually don't have limits, but we usually think we're computing large n asymptotics of functions that really would be traces if n was a positive integer. But in the large n asymptotics, these things aren't really traces. We just call them traces. So one might suspect that these objects could be interpreted as elements of a type 2 algebra whose trace function is what we're computing. Now, an elementary example where you can make this very explicit is JT gravity coupled to matter in space-time dimension 2. So we compute from disk path integrals, for example, with the disk of circumference beta in example 1, or a disk of with boundary segments of length beta 1, beta 2, and beta 3 separated by operator insertions, what we call operator insertions, but we aren't really inserting operators. We're inserting ingredients in a path integral. Anyway, we call the things we're computing traces, even though there's no one-sided Hilbert space in which they are traces. Well, there's no Hilbert space at all in which they are traces. An interpretation is that objects such as e to the minus beta h and so on are elements of a type 2 infinity algebra in which the trace function is computed by a path integral on the disk. Well, what's this good for apart from hanging a plaque on the wall and saying that we've discovered a type 2 algebra? One answer is that although JT gravity does not have a one-sided Hilbert space describing states of a single black hole, it does have a two-sided Hilbert space describing states of an entangled pair of black holes. And in this situation, you can define type 2 infinity algebras, A right and A left, for the left and right boundaries respectively. And you can show that they're each factors, they have trivial centers, and they're each other's commutants. That means A left consists of all operators that commutes with A right and vice versa. The statement that they are commutants means that even though classically there can be a long wormhole between the two sides with a lot of matter inside the wormhole, so I've drawn it schematically here. Now I've drawn a long wormhole between the two sides, a lot of massive particles in between, and the causal wedge of the left and right boundary is very small, and there's a lot of stuff that neither observer can see classically. However, the fact that the two algebras are commutants means that the tensor product is the algebra of all operators on Hilbert space with no gaps. There's nothing in between that's not accessible on left or right, or at least not accessible to an operator with if you have combined access to the left and the right. For example, the renormalized length between the two sides is an operator in A left tensor A right in JT gravity with matter. This is a sort of non-perturbative version of entanglement wedge reconstruction. There's a gap between the two causal wedges, but there's no gap between, roughly speaking, the reconstructible wedge of the left or right, where by reconstructible wedge I mean whatever you can learn about by studying either A left or A right. There's also no known classical geometric description of these reconstructible wedges, except in the usual sort of semiclassical limit. And it would seem that only in the usual semiclassical limit should one hope for such a classical description of what these wedges mean. But algebraically, there's a sort of abstract entanglement wedge reconstruction in the large N limit using these type 2 algebras. This has an interesting variant in n equals 2 supersymmetric JT gravity. In the long wormhole situation, in bosonic JT gravity with any amount of matter in the bulk, the energies E left and E right measured on the left and right can be arbitrarily small, but they can't be strictly zero. However, in n equals 2 JT supergravity coupled to matter, no matter how much or what matter there is in the bulk, there exists exactly zero energy state, a completely supersymmetric state that looks like a supersymmetric ground state to an observer on either left or right. In other words, there can be an extremal black hole, as seen on either side, with any amount of matter behind the horizon. So there's a large space of two-sided extremal black holes, one for every SU1 1/1 primary field of the matter system. This is just the conformal supergroup of n equals 2 JT supergravity. If you take the type 2 infinity algebra that would exist in general and project it to the ground states, you get a type 2-1 algebra that acts on extremal black holes, as essentially suggested here and further studied in a recent paper. Now, in space-time dimension bigger than 2, in theories of ADS gravity with a known CFT dual, we expect that for positive integer n, there's a one-sided Hilbert space Hn, which at high enough energies is a black hole Hilbert space that we don't understand it very well. So, as I've said, we expect these things are really traces if n is a positive integer. The only trouble is that when n is a positive integer, we can't make the statement that the high energy states are black hole states very precise. Such notions that involve causality are tied to an asymptotic expansion near n equals infinity. As I've told you, near n equals infinity, we get answers we can't literally interpret as Hilbert space traces because the Hilbert space Hn does not have a large n limit. What we do have in an asymptotic expansion near n equals infinity is a description by a type 2 algebra. Presumably, the reason that limit is important is that it's the region where we can make contact with semiclassical ideas of causality, which are tied to conceptual questions about black holes and quantum cosmology. JT gravity is different and easier, more tractable for a couple reasons. One is that the analog of n is the number of C of matter fields, and no large C limit is needed in the analysis. And that's good, but then there's something which is bad, that even for fixed C, there's no one-sided Hilbert space. So for the analog of integer n, JT gravity is still in the type 2 situation because of the second fact. Above 2 dimensions, something somewhat similar to JT gravity, with the bottom-up theory of gravity potentially lacking in ultraviolet completion, like pure Einstein gravity, or Einstein gravity with electromagnetism, which potentially, if it lacks an ultraviolet completion, also lacks a well-defined black hole Hilbert space. But nevertheless, to the extent the theory makes sense, we can compute trace e to the minus beta h by Euclidean path integrals, and you could expect to give such results a type 2 interpretation to the extent that the theory makes sense, even if it isn't a truly well-defined theory with a true black hole Hilbert space. Another way to say the same thing is that if you have a continuous spectrum but a finite partition function, that's impossible in the type 1 world. It's impossible in the world we take for granted in ordinary quantum mechanics, where a continuous spectrum implies a divergent trace. But if it's perfectly possible to reconcile a continuous spectrum with a finite trace if the object whose trace you're taking is an element of a type 2 algebra, and by trace you really mean the trace of the type 2 algebra. So whenever you're tempted to think that you have a continuous spectrum and a finite trace, you probably have a type 2 algebra in your hands. Now, a more explicit construction of a type 2 algebra is available in a couple of important cases. One is a two-sided Schwarzschild black hole, and also an analog in quantum cosmology. So for a two-sided black hole, let H be the generator of time translations. So as you recall, the time translations go forward in time on the right boundary, but move backwards on the left boundary. The Hamiltonian H can be written as an integral over an initial value surface S, which I'll take to be at t equals 0, where t is Schwarzschild time. So the initial value surface is that horizontal surface. And we take the vector field V, the Killing vector field associated to time translations, and the stress tensor, and we integrate over S, and we get the generator of a symmetry of the two-sided black hole. In heuristic arguments, you often want to decompose S as a union of S right and S left of portions on the right and left of the horizon. And then you write H as H right minus H left, where H right and H left are the parts of this integral to the left or right of the horizon, where you usually include some minus signs to compensate for the fact that H, to make sure that H left as well as H right are moving forwards in time. Now, in ordinary quantum field theory, this decomposition is not correct. If you try to make it, you run into ultraviolet divergences. Trying to make this decomposition leads to ultraviolet divergences at the bifurcation surface, which is the common boundary of the two regions S left and S right. However, in gravity, there's no problem with the decomposition H equals H right minus H left. In fact, this is just the ADM expression for the total conserved charge H in terms of ADM energies, H right and H left, measured on the right and left boundaries. So now, given this knowledge, let's try to define an algebra of observables accessible to an observer who lives in the region U right, to the right of the bifurcation surface. So, in ordinary quantum field theory, the algebra of observables would be a type 3 algebra A0. But in the presence of gravity, the full algebra of observables has one more generator, H right. So A is the von Neumann algebra generated by A naught together with H right. So this symbol just means the algebra generated by these things taken together. Well, H right is an observable for an observer in the right region because it's just the ADM mass over here. But the corresponding energy H left commutes with all observables in the right region. And the observer on the right knows nothing about what H left is. So let's just give it an abstract name X to emphasize that we're taking the viewpoint of an observer who knows nothing about what H left means. Now, we can trivially write the formula that H is H right minus H left, or H right minus X, in the form H right is H plus X. So taking gravity into account, we can describe the observable algebra in region UR, to the right of the horizon. It's the algebra generated by A naught together with H plus X. So we took the naive quantum field theory algebra and we added one more observable. Here we've run into a classic construction of a type 2 algebra from a type 3 algebra. Takasaki and Kahn in those days were not trying to do quantum gravity, they were trying to understand type 3 algebras. Since type 3 algebras were hard to understand, it was useful to find a way to construct a type 2 algebra out of a type 3 algebra, and in a certain sense the construction can be inverted, though I won't explain that. So it gave information about the type 3 algebra, which a lot of the theory of type 3 algebras was based on. Anyway, the mathematical name is that what we get when we add h plus x to a0 is the cross product of the algebra A0 by the one-parameter symmetry group generated by h plus x. This construction could be defined for any h plus x where h generates an automorphism of the algebra. But in this particular case of time translations of the two-sided black hole, H is the generator of what's called the modular automorphism group of the thermofield double state, as interpreted by Sewell. And the initial algebra was of type 3, so then the cross product algebra is of type 2 infinity. That's basically the result exploited by Takasaki and Kahn by coincidence in what was also the early period of black hole thermodynamics. So if A0 acts on a Hilbert space H0 and H is an operator in H0, then the cross product algebra acts on a Hilbert space which is the original Hilbert space tensored with L2 functions of x, which I'll just call L2 of x. So what Takasaki and then exploited also by Kahn did was to make the Hilbert space a little bit bigger by including functions of one more observable, but an uninteresting observable in the sense that it commutes with everything. And then you add h plus x, where h is a symmetry generator, to the original algebra. And the theorem here is that that produces a type 2 algebra out of a type 3 algebra. And you could make this quite explicit. If psi TFD is the thermofield double state in the original Hilbert space, and psi hat is the thermofield double state times e to the x over 2, then the trace of any operator is its expectation value in the state psi hat. And although I won't show a proof, it's not too long to prove that that does have the properties of a trace. This is a type 2 infinity algebra, not type 2-1, since the trace of the identity, by definition, is the expectation value of the identity in this state, which is the norm of the state. And I assume that the thermofield double state is a unit vector, but the x part of the inner product is this divergent integral. So the trace of the identity is infinite, so this is a type 2 infinity algebra. And physically, that's related to the fact that you could throw in mass and make the black hole heavier and heavier with more and more entropy. So indeed, since we have a trace, we can also define an entropy, and we can also compare this entropy to the usual generalized entropy. But when we do so, we have to remember that the generalized entropy is not defined for all states. It's defined for quantum fields in some state psi in an almost definite spacetime. It's not defined, I'll say what it is defined for. To get a definite spacetime here, we need the canonical conjugate of x, which is a relative time shift between left and right boundaries, to have an almost definite value. So the canonical conjugate of x is a parameter in the spacetime geometry, a time shift between the two boundaries. It needs to have an almost definite value. So a state in which it has an almost definite value is a state of the form psi tensored with f of x, where f of x is slowly varying. We could also more generally let psi depend slowly on x. Those are states for which the usual generalized entropy formula makes sense. And you can show that the density matrix, in this paper we computed the density matrix approximately and showed that for this kind of state, the entropy defined in the type 2 algebra agrees with usual generalized entropy up to an important state-dependent constant, which from this point of view was not defined. Subsequently, the exact density matrix was computed for such states without assuming f is slowly varying. In general, it's hard to use this to compute entropy when f of x is not slowly varying, because it's hard to compute the logarithm of the density matrix. But a highly non-semiclassical limit where x rather than its conjugate is sharply peaked is tractable, as shown in this recent paper. Now, in this construction, it was important, although I whizzed past it too much to give a full explanation, that the two-sided ADS Schwarzschild black hole, or ADS flat Schwarzschild black hole, has an equilibrium state, the thermofield double state. well, I use it in defining the trace, so it, I guess, was clear that we needed it. In important examples such as the Kerr black hole, or Kerr-Newman black hole, or an ADS, or a de Sitter-Schwarzschild spacetime, there's no equilibrium state, so the discussion as presented doesn't apply. However, by starting instead from the Unruh state and operators on the past horizon, you can make a somewhat similar construction of a type 2 infinity algebra for those other spacetimes. And there are extensions to cosmology that I won't have time for, I'm afraid. How much time do I have? What's that? Okay, well, I'll be very quick in finishing. So this has an analog for de Sitter space that I actually think is more interesting, but I guess I don't have time for, because de Sitter space is less understood than a black hole. So here, see, for ADS, for the black hole, we actually could be looking at it from outside the universe. But in de Sitter space, it's a closed universe, so we have to look at it from inside. And therefore, we really have to consider the perspective of the observer and the observables that can be measured along the observer's world line. Unfortunately, I promised one of the panelists to say at least a word or two, but there isn't really time for it. In ordinary quantum field theory, we would again have a type 3 algebra for the green patch. And since it's a closed universe, the operator I called H would be a constraint operator. That means that only H invariant operators are allowed, so naively we should take the type 3 algebra A0, replace it by its H invariant subalgebra A0H. That doesn't work. A basic result in ergodic theory says that only C numbers commute with H. To get a sensible answer, we have to take seriously the fact that the reason we're interested in the static patch P is that there's an observer there. We need a model of the observer. The simplest model is that the observer has a rest mass plus a Hamiltonian of the observer's apparatus. We'll assume that if for M to be the mass, observer's rest mass, Q is bounded below by 0, but otherwise we give Q a continuous non-degenerate spectrum. So the Hilbert space of the observer is L2 of Q, where Q is non-negative. For the moment, we ignore the constraints and use the canonical conjugate P. I'm really going to finish as quickly as I can, but want to make it possible for Chris to continue as he's intending. So the naive algebra, including the observer, is obtained by adjoining both Q and P to A1. But then we have to impose the constraints. And the constraint generator now includes the H of the spacetime plus the H of the observer. And now there is an interesting answer for the algebra of observables along the world line. And it can be described quite explicitly. It's generated by conjugated versions of the ordinary operators A, which you can think of as operators addressed to the world line, plus one more operator Q. And by conjugating by e to the minus IPH, you can show that this is, again, the cross-product algebra as defined earlier of type 2 infinity, but the constraint tells us that we should include a projection operator into states where Q is non-negative, and then the algebra we want with the projection operator before and after turns out to be of type 2-1. So that's a type 2-1 algebra appropriate to an observer in de Sitter space, and because it is of type 2-1, there's a maximum possible entropy. The state of maximum entropy is the maximally mixed state with density matrix 1. Concretely, it's empty de Sitter space now with the observer in equilibrium at the de Sitter temperature. So as was guessed, this justifies what was guessed long ago in purely thermodynamic grounds with no microscopic notion of entropy, that empty de Sitter space is a state of maximum entropy. So thank you for your attention, and my apologies for going over.
Okay, let's take a couple of quick questions so we can move on to the panelists quickly. Eva.
So thanks for the great review. It's everything we hoped it would be. I want to make a comment / question, which is, as you said, this global de Sitter space has no time-like boundary, and you've built in an observer that lives within that space-time. However, It does not follow from the positive cosmological constant that there is no time-like boundary in de Sitter. You can consider the possibility of a time-like boundary with positive cosmological constant. When you do that, the Hamiltonian is not constrained to 0. You have a notion of an energy spectrum, and many of the features of the space become more similar to the ADS-CFT case. This will be explored later in the week on, I think, Thursday morning in talks of Aninos and Toroba. But I think it does fit into this session as well. So, yeah, if you have any comments on that, they'd be welcome.
Oh, I only will make a brief comment, which is that if you wanted to think of the observer as having a non-zero thickness, I modeled the observer as a geodesic. But if you want to think of planet Earth as the observer, all of us here on planet Earth, then planet Earth sweeps out a tube in space-time, and the surface of planet Earth could be your time-like boundary. So in the case that your time-like boundary is small compared to the de Sitter horizon, you could think of it, the time-like boundary itself, as being the observer in my discussion. And then you could equip if you have more operator, in the model where the observer is seen as planet Earth, of course, my model of the observer was rather crude.
Well, I agree. There's some pretty good analogies between the two, but I think they're mathematically distinct. Either there's a notion of energy or there isn't. And if you have a time-like boundary with a well-defined boundary condition, for example, Dirichlet is actually well-defined in this case of a small spherical boundary, then you have a notion of energy which is, it really is distinct from planet Earth, which has a mass.
Well, in my presentation, the energy of the observer was mc squared plus q, which was a well-defined element in the algebra. So there was a well-defined notion of energy for the observer.
Okay, they're closely connected. I'd love to discuss this further.
Okay.
Okay, I propose that, okay, maybe Lenny wants to ask a quick question.
I'm not sure if this is a question or a comment or a complaint, but no real observer can last forever.
Yes.
They'll eventually either evaporate into the horizon
Yes.
or fall into the horizon. So if I take a state with an observer and I assume that that observer is described by the same physics as everything else,
Yes.
it'll last a finite amount of time.
Mm-hmm.
In fact, if you run it backward, it'll also fall into the horizon. So the only conclusion would be that an observer is a fluctuation, a fluctuation which occurred in the thermal state, which occurs extremely rarely. If you ask how likely it is that such a thing can happen, it's incredibly exponentially small. And so it means that the amount of time that an observer is present in de Sitter space, I'm assuming eternal de Sitter space.
Yes.
That amount of time is negligible, very, very tiny. Don't we have to be able to describe all the rest of time in which there's no observer there? And if so, how do you do that?
Well, first of all, I certainly agree with you that an eternal observer was an idealization. I think what's really required is an observer with a lifetime long compared to the de Sitter, the cosmological timescale, which is
it
realistic.
depends on what your focus is. If my focus is a really global description of the eternal time,
Yes.
then
No.
then we're going to be forced to some kind of theory which describes some kind of system
Yes.
in which fluctuations can happen, observers can come and go, and then we can ask conditional questions. What's the probability of such and such given that there's an observer
Yes.
there?
Well, certainly what I have described would be described more fundamentally along the lines that you say.
Yeah, we've talked about this a lot in the past, but it does suggest that some kind of theory which is independent of the existence of the observer ought to exist and be capable of describing the fluctuations in which an observer comes and goes and spends a tiny, tiny fraction of the time existing.
Perhaps. That'd be nice.
Okay, I propose we move on. So let's move to let's thank Edward again. And we're going to have our first panelist, Hong Liu, come up. He'll give a short talk.
Yeah, okay. Yeah, thanks, Edward, for the very beautiful lecture. So I would like to highlight some aspect of this algebra thinking for understanding more narrowly just holography in the context of the ADS-FT duality. Oh, sorry. No, it doesn't do anything. Still not hearing. Okay, yeah. Yeah, so I would like to talk a little bit about how, in the context of holography, the causality and the Bach locality emerges from the boundary theory. So now we have two ways of understanding emergence of Bach space-time, say from the boundary theory. So one way is a familiar one, is the Bach space-time. Say, let's imagine this is a boundary, and then there's a radial direction, and then the scale in the boundary theory then is due to the radial direction. And the Wilsonian RG flow in the boundary theory then can be understood as the radial evolution in the Bach. And then if we are powerful enough, say, suppose we can solve the incontforeseeable Yang-Mills theory as John coupling and large N, then we can in principle reconstruct the Bach space-time using the normalization group flow. And say, in principle, we can reconstruct the Bach geometry and Einstein and the matter actions, etc. So this is a very beautiful story. But however, in this approach, many other aspects which we would like to know are not manifest. For example, the local physics, causal structure, and the entanglement structure, they are all not manifest. And the reason is that this kind of concept, they have to do with subsystems. So let's imagine, let's now see the ADS as a cylinder, and consider some, say, sub-regions O1, O2, O3. And the local physics has to do with what operations you can perform in such kind of local region. And the causal structure has to do with the relation between those regions. For example, the operations in O1, say you suppose O1 and O3 are space-like separated, then the operations in O1 should commute with those in O3. And similarly, entanglement structure relates corresponding to subtle correlations between, say, degree of freedom in O1 and the one outside. Okay. And in order to understand those aspects, the emergence of those aspects in the manifest way, to understand the emergence of space-time, then we need to understand the emergence of all Bach subsystems. So we need to have a formulation so that the emergence of the Bach subsystems are manifest. And so this has been, we have proposed a proposal to do this. So this is called sub-region, sub-algebra duality with Simon Neuthauser. And the basic idea is that there's for each Bach sub-region, there's a corresponding emergent boundary type 3-1 von Neumann algebra in the large N limit. And for example, say, again, this picture, you have O1, O2, O3. And then, say, for example, O1 then can be described by some boundary algebra A1, which captures all the physical operations you can perform, say, in O1. Okay, similarly, you can do this for O2 and O3. And now the relation between all this kind of relation between those subsystems in the Bach then can be captured by the relations of the corresponding boundary algebras. For example, the O1 is a set of O2, then corresponding to the corresponding algebra A1 is the sub-algebra of A2. And say O1, O3 are space-like separated, so this encodes the Bach causal structure, and this is related to their algebra, corresponding algebra commutes. So in the boundary theory, say if you have two operators space-like separated on the boundary, of course they commute. But this commutant structure is actually more general than the causal structure on the boundary, because you can also have time-like separated operators, say take the superposition of them, they can turn out to commute. So this commutant structure is more general than the boundary causal structure. And turns out that this larger commutant structure, what this encodes is this Bach causal structure, of this one higher dimension. And similarly, the fact that we can sharply define some kind of sub-region O1, and this is implies very specific Bach entanglement structure. It's because any sharply defined region, then near the boundary of that region, locally is like a windowless space-time. And the local windowless space-time implies a very specific Lorentz structure and then the entanglement structure. And then this is reflected on the boundary side in this emergent type 3-1 structure. Okay. Yeah, so in the boundary theory, degrees of freedom, they are entangled with each other. And that kind of entanglement depends on the number of degrees of freedom, say this n, parameter n. And as you take n go to infinity, those entanglements go to infinity. And in the limit of entanglement going to infinity, then there's a new structure emerges, and that kind of new structure precisely then captures this kind of windowless structure in the Bach, corresponding to this kind of entanglement structure in the Bach. Okay, so I will just very quickly end with some philosophical remarks. So this sub-region sub-duality is reminiscent of this so-called Gelfand duality, which provides a description, say if you want to describe a topological space, an equivalent way to describe a topological space rather than geometrically, you consider the algebra of functions on that space. And you can show that the algebra of functions on that space encodes all the geometric information of that space. And this is the starting point, say, of formulating more general geometry, say, for example, non-commutative geometry. So this provides a more flexible way to think about geometry. Because these kind of algebras are commutative, but when you consider non-commutative algebras, then that can help you to describe non-commutative geometry. So this kind of sub-region, sub-algebra duality is like a generalization of this kind of non-commutative geometry that you use the algebra to capture the Bach space-time and all the physics in that space-time. So this provides a powerful and more flexible language to talk about Bach space-time and the physics in it. And in principle, this also potentially including the stringy or quantum gravitational regime. Okay, so I will stop here.
Thanks, Hong. Okay, if there's any urgent questions, maybe Nima can set up already. Urgent questions? Okay, let's thank Hong again. And next up is Nima Lashkari.
Thank you so much for the invitation and the opportunity to speak here. I'll be very brief, of course, for a couple of minutes. And thanks. I would like to start by thanking Edward and Hong for setting up the problem review. And what I will say is actually just a small, the way I think about this problem, how algebras can help us learn about quantum gravity. I'll try to make one point, if I have my slides. All right, okay. So I'll start by introducing a notion that I consider to be important in this story, the notion of future algebra. So imagine the set of all observables we can measure from now until eternity forms a proper subalgebra of observables. For that to happen, it has to be that Hamiltonian is not an observable. When that happens, we call that a future algebra. So there is this important theorem, the BW theorem, that tells you that modular flow of a wedge is boost. So if you put these two together, you can build an example of this future algebra by considering these wedges in two-dimensional or higher dimensional flat space, where this is A, region A, this is the larger region B. The algebra of region A with respect to the modular flow of B is a future algebra. Right? So that's the concept. So this allows for a characterization of a wedge in terms of just abstract algebras. You have a region A that's inside B. This is a modular future algebra of B. This inclusion of algebras is a modular future algebra. You can have C inside B. This is a modular past algebra. And with some extra condition on the intersection of A and C, you can actually algebraically encode or see the wedge in some abstract algebras. Now, let's take a step back and think about what local quantum field theory is. One way to think about local quantum field theory, at least in flat space, for example, is to think about a map from wedges to operator algebras. So this map respects inclusions. It sends region inclusions to algebra inclusions. Symmetries are represented by symmetries on the symmetries on the Hilbert space. And then there's a notion of causal complement, which is replaced by modular conjugation. The idea is to go in the opposite direction. If you want to see a space-time in some abstract algebras in lines with what Hong was mentioning, seeing some geometry in some abstract algebras, you can imagine a set of algebras, or more mathematically, a net of algebras labeled by some abstract labels, A and B's. And you have a notion of inclusion that you want to, if there is a space-time in it, you want to map it to some inclusion of regions. You have the notion of symmetries that should be related to symmetries of the space-time, and you have the notion of causality or commutation relations that tells you about causality in space-time. This sort of gives you an algebraic characterization of stringy spacetimes in terms of modular flows and conjugation of future and past algebras in the example of ADS, eternal black hole. But this principle is a lot bigger. So I just want to say that here's a list of some explicit results in this direction. There was an algebraic characterization of stringy horizons. There was a discussion of local Poincare group, and more recently, a characterization of stringy ADS2. I just want to end with this slide, mentioning that there is a very, very nice connection between what I just described and the so-called ergodic hierarchy. So if you're thinking about some sort of abstract dynamics, there is a hierarchy of how chaotic systems are, strong mixing, K-systems. You don't need to know what the definitions are, but this is sort of standard textbook definitions. You get, as you go in this direction, they get more and more chaotic. And algebraically, there is a map, or at least a guideline, for what these correspond to. So I'm just flashing this in case people are interested in asking questions, or, yeah. So this is basically the big picture. Thank you so much.
Thanks a lot, Nima. Okay, so are there any urgent questions? Chris can get set up while we... Okay, it doesn't seem so. Let's thank Nima again. Okay, and our next panelist will be Chris Fewster. Okay, take it away.
Okay, well, thank you very much to the organizers for the invitation and to Edward for the review. I'm going to pick up on one particular aspect of what Edward talked about right at the end, in particular this CLPW model. And I'm going to try to put that in a broader context, and this is based on work with my colleagues in the paper just given there. So just to remind you briefly of what the CLPW model was about, we were in de Sitter space. There was the static patch here, and the observables on the static patch form a type 3 von Neumann algebra. And then what happened was that a very simple and specific observer system was invoked. Then, in the presence of gravity, the total Hamiltonian was regarded as a constraint, so that only the invariant elements of the joint algebra should be regarded as actual physical observables. And the important observation is that the resulting algebra is of type 2-1 in this situation. So the questions that we were interested in is, well, how fine-tuned is this observer system? It's a very particular dynamics that was given. And also, how essential is gravity in this story? So starting with gravity, I think it's true to say that the use of the total Hamiltonian as a constraint really comes from the theory of linearization instability in gravity, going back to works of Moncrief and others. And that would suggest perhaps that gravity plays a decisive role in what's happening here. But in fact, we would argue that it's natural to restrict to isometry invariant observables, even for quantum field theory in a fixed curve space-time background. And this is really the fixed background remnant of the whole argument. And the whole argument applies not only to general relativity, but in fact to any generally covariant theory. So sometimes the whole argument is summarized by saying that general relativity is pointless. If general relativity is pointless, then quantum field theory in a curved space background should really only have points modulo isometries. And normally that is ignored in quantum field theory in curved space-time, but here I would argue that one should actually remember that fact. So what we were also wondering about the CLPW observer is because it's not coupled to the system, you could ask the question, well, what, if anything, is it actually observing? And I wonder if that actually relates to one of the questions that was asked earlier. So what we did was to start again from a description of measurement theory in quantum field theory, which is something that I've been working on with Rainer Fesch for a few years. So in this setup, the quantum field theory is measured by coupling it to another quantum field theory, a probe theory. Now we have the situation that isometrically related couplings should be indistinguishable. So how do we resolve this ambiguity? Well, we introduce a gadget which is called a quantum reference frame. I won't tell you quite what one of those is, but I will tell you, however, that the CLPW observer can easily be given the structure of a quantum reference frame. So this really generalizes what's going on in their paper. Now, the quantum reference frame is, broadly speaking, telling you where you're going to make the measurement. It's like a clock or something more general sort of a system that triggers the experiment. Exactly what the reading is of the QRF has no intrinsic physical significance, but again, one can argue that the invariant elements of the joint quantum field theory and quantum reference frame algebra are the physical observables. And that gives us a framework where we can investigate in generality what conditions are necessary for the change in type of the von Neumann algebra. So I'm just going to give you a very quick idea of our results. If G is the isometry group of the space-time M, we're going to assume that compact subsets of the space-time are stabilized by compact subgroups of the isometry group. And then any quantum reference frame that's capable of resolving the orbits of the group turns out to have a very particular form. And we can classify all possible such quantum reference frames using Mackey theory. And this allows a full classification, or computation rather, of the algebra of invariance, which is what we're here. So this is really just to illustrate that there's some actual mathematics in what we were doing. The quantum reference frame can be classified essentially by putting it into a very standard form. And to get back down to the original one, there's a projection. Now, upstairs here, it turns out that one can compute an enlarged algebra of invariance, and this is where the cross-product construction that Edward mentioned takes place. To come back down to the actual algebra of invariance, it turns out that the right thing to do is, again, use a compression using essentially the projection that came in the QRF classification. So this is really a generalization of what Edward was saying. And when he, quote, when he describes it as forgetting about the constraint for a moment, this is in fact passing to this upstairs picture of the dynamics. So then we can actually look at the type of the algebra invariance in a particular situation where the group is just the reals cross some compact H, and we have a sort of, we have modular action, that the time flow is a modular flow. Then it turns out that you always have a change in type from type 3 to a semi-finite type. So it's not type 3. And in fact, it turns out that the algebra invariance is finite, so that would correspond to type 2-1 usually, if the quantum reference frame admits a particularly well-behaved KMS weight at the temperature of the de Sitter temperature. And this effectively constrains the growth of the number of degrees of freedom in the quantum reference frame with energy. So to summarize, what I think we've done here is to generalize the CLPW model, put it in a broader setting, which is operationally motivated, and hopefully elucidates the roles of both gravity and the thermodynamics of the observing system. Thank you.
Thank you, Chris. Okay, so maybe the panelists can come up, and while they do that, are there any urgent questions for Chris? Okay. Okay, let's thank Chris again. All right, so I was thinking I would start the panel off with a very broad question, and maybe they can discuss, and then I'll open it up to questions from you guys. So the question is, what are the main lessons or advantages gained from the operator algebra approach to gravity versus, say, more traditional approaches like the path integral or quantum information, like standard quantum information approach? So who wants to take it away?
Okay.
Go for it, Hong.
Yeah, I will start. So von Neumann algebra operates in a different regime from the standard quantum information approach. So standard quantum information approach applies to situation which you have finite amount of entanglement between different subsystems. So in that case, you can factorize the Hilbert space, then define the density operator, etc. So it's what Edward called type 1 situation. But there are many situations, like in quantum field theory, in statistical system, or just in the quantum mechanics in the Lagrangian limit. Then you have infinite entanglement. And then, when you have infinite entanglement, then the factorization of the Hilbert space break down. Then the standard technique cannot be used. So if you want to describe entanglement intrinsically in this kind of infinite entanglement situation, then you have to use von Neumann algebras. There's no other way. Yeah, at least this is one basic fundamental way which von Neumann algebra can help.
I can also mention one thing, at least for me, when one thing that was interesting learning about operator algebras in the past couple of years is that operator algebras, von Neumann algebras, come intrinsically with a notion of dynamics. This is modular flow. So, of course, if you talk about density matrices, you could talk about modular flow, but within the conventional theory of quantum information of finite quantum systems, modular flow or modular conjugation, which is another symmetry of operator algebra, von Neumann algebras, has not played the prominent role, but operator algebras bring these to the center of the focus, and we extensively use particularly the analytic properties of modular flows. So these are very powerful analytic tools that I think at least, well, they generalize to arbitrary dimensions, at least in my experience. One thing that surprised me was within the context of operator algebras, proving monotonicity of relative entropy is a lot easier, or monotonicity of a bunch of other important information theoretic quantities. So even though they interact, but the analytic tools are sometimes more powerful.
Maybe I'll comment. So I actually come from the algebraic quantum field theory community myself, so I have a different perspective on things, really, which is, of course, that AQFT gives you a very, very general way of describing quantum field theories. It's actually reasonably low input. You're just making assumptions about the fact that there are algebras describing local observables and some basic principles about how they should be formulated and how they are related in different parts of space-time. So I suppose that one thing that I noticed with these developments in string theory and quantum gravity is, of course, now you have access to the wealth of literature in AQFT going back into the 1950s with works of Haag, and then we've already heard about Araki and Summers and others. So I think you're opening up a huge treasure chest, really, of literature coming from the AQFT side.
Edward, do you want to comment?
Since I had the chance to try to answer the question in my review and went over, I think it's not really proper for me to take very much time now. I would just say briefly, as I did during the review talk, that I think the algebraic approach may be necessary when you want to do quantum mechanics while also having semiclassical spacetime and causality. I think that combination possibly forces you into this world.
Okay, thank you. Maybe I should open it up to people in the crowd, because I'm sure they want to ask questions. So there's a question over there.
So I have a comment and a question. The comment is related to the discussion that Eva and Edward had earlier about observers. So I think there isn't this dichotomy between having the observer as a world line or introducing the observer as a particle. One could instead just think of the observer as in heavy excited state. So you think of de Sitter space, you impose all the constraints, and then just think of heavy excited state on top of the Hartle-Hawking state. And in the limit where you think of additional excitations that are much lighter than the mass of this observer, you would recover both the type 3 structure and also the type 2 structure if you included gravitational corrections. And the state doesn't have to be very heavy. It could be something that's much lighter in Planck scale and much heavier than cosmological scale. So it doesn't even have to be the Earth. It could be a virus, for instance, which would work well as an observer. And so you don't need to introduce the observer externally. That's just one comment, probably obvious to everyone in the panel. The question is an open-ended question, slightly different. And the question is, in our world, we are not really in the situation where we have n going to infinity. So maybe a more accurate description of the situation we are in is that we have access to a restricted set of observables. We can measure A and B, but maybe we can't measure the product A and B. Now, this is an uglier mathematical structure because it doesn't have a product defined in it, so it's not really an algebra. It's an algebra with cutoffs. But do you think we could make some progress by thinking about this kind of a mathematical framework where you have a set of observables with a limited product, but also cutoffs? And how much do you think would carry over to something of this kind, which doesn't allow some of the nice mathematical techniques that you have when you have a true algebra?
So do you have a specific questions in mind which motivate that mathematical? Do you have a specific physical setup in mind which motivate that mathematical?
I think the specific physical setup is our world. In our world, we have access to some set of observables, but we can't. You might be able to measure a 10-point correlator, but you can't measure maybe a 100-point correlator, even though you could multiply 10-point field operators with each other to get 100-point correlators. So it's really our world where this is where we are in. We are in a situation where we have cutoffs and not really algebras. So it's probably a more accurate description of our world.
Well, maybe I can add a comment because I've thought about similar problems. If you do start with an algebra, a natural way of talking about what you called an algebra with a cutoff or a sequence of operator systems that limit to an algebra could be in the context of quantum error correction. So you could define a noise map that basically washes out those operators that you don't like. For example, a phonon creation operator to the power of a gazillion. Then within the context of quantum error correction, operator algebraic quantum error correction, this is a very well posed problem. And I actually want to highlight a paper recently, maybe from last year by Kitaev, which was about approximate quantum error correction exactly in this context. So these are approximate conditional expectations.
So maybe another comment is that I think partly behind what you're saying is that there are things that we won't necessarily know, like the 100-point correlator I think you mentioned. I think we have to decide what sort of idealizations we're comfortable with in mathematics. Because you could say, well, we never measure down to arbitrarily small distances. We only measure finite distances. So maybe calculus should be thrown out. But we wouldn't tend to do that. We tend to use calculus because it's a very useful tool, and it gives us very good insights into the real world. So I think that sometimes in mathematical physics, we use structures which, okay, are definitely idealizations of the real world. We use them because they've proven to be useful. So I wouldn't necessarily say that we have to throw away the algebra concept just yet. It's a very similar situation, perhaps.
Just to add, the limits here are interesting because they're the limits where, causality and so on break down, our semiclassical notions of space-time breakdown. So there's an idealization, of course, which is relevant, but the limit where it breaks down is interesting, which is why I was asking this.
Actually, I want to make one small comment. I can't say anything useful about cutting off the algebra, but if you want to incorporate the idea that the observer can't make measurements of arbitrary resolution, there's actually a simple way to do that in the context of the model I was presenting. I took Q to be bounded below by 0 because it's unphysical to say that the observer's energy has no lower bounds. But if we simply took an upper bound on Q, everything I said was essentially true, except the projector pi should incorporate that. And then you find that the observer can't make measurements of arbitrary resolution. The resolution the observer can achieve is conjugate to the upper bound on Q. So that's a simple way to remain in a mathematically tractable world, but incorporate the idea of an observer who can't make measurements of arbitrary resolution.
I have a similar question to Suvrat, but not about resolution. So if you're an observer, right, and we say, okay, there's time-like tube theorem, which says that the algebra is type 3, which is fine in QFT, but as an observer in a gravitational system, so to get time-like tube theorem to work, you need out-of-time ordered operators on the time-like tube, right? And as an observer in gravity, I can't turn back time and measure and multiply operators in the wrong time order. I only have access to time-ordered operators. So is this not a problem for thinking about algebras and gravity?
I'd actually like to comment on that. So first of all, you asked if there's a time-like tube theorem with gravity. Presumably no. You see, without gravity, the time-like tube theorem says that the observables on the world line are the same as the observables in the causally accessible region. With gravity, you can't define the causally accessible region. So the version of the algebra where it's the algebra of a region, I think is going to be ill-defined with gravity. So I think the correct algebra to consider for people like us, observers in the universe, are the algebra of what we can actually measure. And so the motivation for the reason for mentioning the time-like tube theorem is that it tells you that without gravity, we're in fact talking about the algebra of a region. With gravity, when that isn't well defined, we can still talk about what we actually do in the real world, the observables along our world line. Your comment had another point, half, which I had a thoughtful remark about, but now I can't remember it. If the others go on, maybe I'll come back to me.
Sorry, I think my main issue was needing out-of-time ordered correlators for something that's even approximately...
Yes. I worried very much about out-of-time ordered correlators, out-of-time ordered observables. So the fact that we cannot go backward in time, is that an obstruction to measuring OTOCs? I was a little bit surprised to realize that it's not. If you take von Neumann's model of a measurement, you can discover that without ever going backwards in time, you can measure out-of-time ordered correlators. Roughly speaking, you store the value of a field phi at time t in an auxiliary quantum register, but you don't look at the register. and then you go on and store other things at other registers. And after you've stored everything you want to measure, you do it whatever you want. That's the best I can say in words. But I believe that the answer to your question is that according to standard quantum measurement theory as described by von Neumann, for example, there's no problem with the OTOX. That surprised me and almost disappointed me, I must say.
Thanks. Yeah.
Okay, maybe Daniel wants to say something.
Yeah, so Edward, you motivated some of the type 2 structure by using the path integral. But the path integral actually knows a bit more because it can compute the value of entropy, not just the entropy difference. So do you have any comment on that?
Well, unfortunately, I had prepared too much material in my talk, so my comment on that is in slides that weren't presented at the end, but they'll probably be on the conference website. But remember that in proving the generalized second law, Aaron Wall said you should define entropy as the relative entropy with the Hartle-Hawking state of the black hole, the equilibrium state. And if we define entropy as the relative entropy of the observer state with the Hartle-Hawking no boundary state of the universe, and we don't normalize the no boundary state, we take the no boundary state as it naturally comes from the path integral, which I think we should do because we don't know how to normalize it, then that includes the 0 point of entropy. So that was the thought I had wanted to conclude my talk with, but
Okay.
You gave me the chance to say it.
Okay, I think we're out of time, so let's thank the panelists again. Hong, do you want to show a slide? No? No? He doesn't. Okay. Okay, thank you.